Okay, we're going to go ahead and take a look at solving a system of two linear equations in two variables through graphing. We'll take a look at a couple problems. Hopefully I can fit everything in the video all at once. The first problem that we're going to take a look at is going to have the following system. We're going to have 2x plus 3y is equal to 0, and then we will also have 2x plus y is equal to 4. So in order to graph these, what I strongly suggest doing is to get these in slope-intercept form, or in other words, the form where it's y is equal to mx plus b, where m represents the slope of the line and b represents your y-intercept. So we'll go ahead and we'll start doing that. And we would have 2x plus 3y is equal to 0. And what I would suggest that you guys do is to pause the video and get these into slope-intercept form to make sure that you have that scale down. This is something that you should have practiced and had underneath your belt already. Also, probably have a sheet of graph paper, or if you have a really steady hand, you can go ahead and draw a graph by hand on a sheet of blank paper or notebook paper. So we will go ahead and subtract 2x from both sides to get 3y is equal to negative 2x. I could put the 0 in there, but it's kind of unnecessary information. If I note that 0 really has a value of nothing, then I don't have to write down anything. We can finish this off by dividing both sides by 3. So then we have y is equal to negative 2/3 times x. And we do the same thing for our other equations. So 2x plus y is equal to 4. We will subtract 2x from both sides. And now we have y is equal to negative 2x plus 4. Okay, so then we would come to our graph. And I apologize that mine looks a little bit crooked. And we are going to go ahead and graph this. So we'll look at our first one that we have in green. And since we don't see the y-intercept, or if you really wanted to, or if you already had, if you left 0 there, that tells me that I'm going to start at my origin. And then I'm going to, according to the slope, I'm going to move down 2 and to the right 3. 1, 2, 1, 2, 3. And then 1, 2, 1, 2, 3. Okay, you can do as many of these points as you wish, but if you have enough, then you can go ahead and connect your points. And then we would go ahead and do the same thing for our second equation in the system, which we have in red. And that one has a y-intercept at 4, and its slope is negative 2. So if you need to, go ahead and rewrite negative 2 as a fraction. So think about that. How would I write negative 2 so that I can clearly have a numerator and a denominator available? And if you suggested, well, negative 2 is the same thing as negative 2 over 1, you would be correct. And if we have a slope of negative 2 over 1, we would say that we would move down 2 to the right 1. And again, that's because the negative, in this case, we've attached it to the 2, and the 1 is a positive 1. So the positive 1 tells us to move in the direction to the right. So we will go down 2 to the right 1, down 2 to the right 1, down 2 to the right 1, and I can keep going for however many times I wish. So if we go ahead and connect that. So now our solution is going to be where the points intersect. Okay, that is a common point that they both share. So if the point exists on both of the lines, then that means that it would give us true statements when we plug those values into each of our equations in our system. So if you notice, it looks like we have a point at 3, -2. In order to check that, you would, again, plug those values in, and we would see if that gave us a true statement. So if we do a check, we would do 2 times 3 plus 3 times -2, and we would want to know if that equals 0. Well, in this case, I think that that's correct, because we would have 6 plus -6 equals 0, so that will check out. And then if we did 2 times 3 plus -2, does that equal 4? Again, we could say yes, because 2 times 3 is 6. 6 plus a -2 will give us a positive 4. Okay, so let's move on to the next equation. And we will go ahead and look at the system that we have. We have x is equal to 3 minus 2y. And then we also have 2x plus 4y is equal to 6. Okay, so again, we will do the same thing. So what I would suggest, pause the video and get these into slope-intercept form. In other words, get y on its own or isolate it. Okay, so if we start with the first one, I'm going to subtract 3 from both sides. So now I have x minus 3 is equal to -2y. I will divide each term by a -2. So this is going to give me -1/2 x plus 3/2 is equal to y. When you guys solve for slope-intercept form, it doesn't matter if you have the y on the left hand or the right hand side. The only thing that you want to make sure that you have is y completely isolated on one side of the equation. Okay. Then we'll go ahead and we'll take a look at 2x plus 4y is equal to 6. Subtract 2x from both sides. And 4y is equal to -2x plus 6. Divide everything by 4. And this leaves us with y is equal to -2/4 x plus 6/4. But we can clean that up further. So we can say that this is y is equal to -1/2 x plus 3/2. So stop for a second. Take a look at the left-hand side of the equation that we have in blue. Take a look at the right-hand side of the equation that we have in purple. What do you notice? If you're noticing that the slopes are the same and the intercepts are the same, we can actually conclude, and we don't actually have to graph in this case, that these are the same lines. And what you want to note then is if they're the same lines and you were to graph this, it means that both lines are going to lay right on top of each other. So that means that they have all of their points in common. And this is why we can say that this is infinitely many solutions. I'm going to go ahead and use the old excuse that I'm a math teacher and not a English teacher, so that's why I made that error. Hopefully you buy that. So if you were to go ahead and graph this, you would again see that all the points are going to lay right on top of each other. Our solutions are where the lines intersect or touch. So if they're laying right on top of each other, all of their points are touching each other, and therefore all of their points are possible solutions. And since lines extend forever in both directions, we would say that there are infinitely many, because the lines go off in their directions infinitely forever. And that's redundant. But there you go.